time for if you don't,
15 minutes.
15 minutes?
15 minutes? You could have locked the doors.
Yeah, we were not strategizing.
Yeah, you got to think a little bit more
Calvin,
devious.
that's your fault. Should have thought of that.
I know some people come there once in class. They're coming, they're coming.
Really?
Yeah, I don't know why.
Because we have
What? Oh yeah. I don't think it'll work. I don't think it'll work this
What's up,
time.
bro? You doing? Good, good. You get here? Oh, no. Yeah.
What do you have these?
This? Oh,
What are you doing today?
no, I'm finished. I switched my bags. Like, I don't have the laptop bag anymore. Yeah.
I know, they should open at 7:30 so people can get stuff before classes. Yes. Oh yeah, I have a laptop. So what's the word on the street about the final?
Take home. It's going to be embarrassing. That's because you're here today.
Yeah,
If you had
just
if you had locked
us
the
get the
doors,
take-home
yeah.
final,
If
see?
you had locked the doors, there would be no
Just the people who show up on time get the take-home final, right? So Ariana doesn't.
Hey.
How far do you drive, AJ?
You drive C.
I
Yeah.
drive 10 minutes away.
AJ, you really want to go there?
Actually,
We're
You
kind of
wanna
surrounded
pick a
right
fight
now.
with a bunch of fight
Take it.
Yeah.
I don't recommend it.
I know you can't win, right?
Not here, brother.
Tell him no. He's like, stay in his lane.
Yeah.
We got all excited when you said kick one finals.
Yeah, I'm just giving you a couple minutes to kind of
Okay.
calm down. All right. So today we make the transition to finally being able to do what we wanted to do, which is build a regression model. So today we do correlation, and then next week it's regression, and that's it. Okay, and a regression is the model that allows us to predict, or at least to be able to determine what variables, more than one variable, can we have in a model that can account for the proportion of kids receiving preventive dental care in 2016. Okay. So to build this linear regression model, we have to understand what correlation means. That is when we have two variables measured on a ratio scale that track with each other. Okay? And when we say track with each other, I'm going to skip over this part. When I say track with each other, we are talking about, if you were to put the observations on a scatter plot, getting some kind of pattern. And the pattern can be linear or nonlinear. And the correlation that we're going to do today assumes a linear pattern or a linear relationship between the two variables. Now, if you look at these two variables that we have here, this is 2015 density of dentists per 10,000. And on the y-axis, we have the proportion of kids receiving preventive dental care. The scatter indicates a pattern. Now, some might say that there's probably a very weak positive or positively sloped pattern. And yes, there is a weak positively sloped pattern. But our goal is to try to determine if that pattern is statistically significant or not. Now, some of you spend a little bit more time looking at this, which is called a scatter plot, and you'll notice that, well, in the beginning, that is from about 4 dentists per 10,000 to about 6 or 6.5 dentists per 10,000, there does appear to be a positive linear slope. But then after about 6 or 6.5 dentists per 10,000, there doesn't appear to be positive slope. It seems to be a bit more horizontal. How many of you see that pattern? Where there appears to be a linear, positively linear pattern in the beginning, and then it seems to level off. Okay. And I would agree with you. And if we do try to model that, that is linear here and then no pattern here, this would be a non-linear relationship. Okay? Almost like a parabolic relationship or a quadratic relationship, at least the first half of it, where it comes up and then levels off. Comes up and then levels off. But we're going to model it as a linear relationship. That is from 4 to about 9 dentists per 10,000. That there is a straight line that we could fit here, and that straight line would have a positive slope. So we can do this with any variable that's measured on a ratio scale, or two variables measured on a ratio scale, and assess them for whether they share a linear relationship. And there are two kinds of linear relationships that we're looking for. The first is a positive linear relationship. That is where the slope appears to be positive. As x increases, y increases too. The second linear relationship we're looking for is what's called an inverse or negative relationship. That is, as x increases, y decreases. They go in the opposite direction. Okay? So we can only model these two with the statistic that we're going to learn today called the Pearson correlation. Pearson can only test for linear relationships. Your data, as we have here, might demonstrate a non-linear relationship, but we can't use Pearson for that. We have to use other tests. We won't learn about those today, though. Only Pearson. So when we try to associate the density of dentists with the proportion of kids receiving preventive dental care, using a different program here, we see that the Pearson correlation value is 0.319. Now this statistic, the correlation value, Pearson correlation, ranges between 0 and 1. Or actually -1 and 1, but it's 0 and 1 in terms of absolute value. And the closer to 1.0 you are, the tighter the relationship, the tighter the linear relationship between these two variables. The closer to 0 your correlation is, the more random the relationship is between those two variables. So here, we're at 0.3. Not close to 1, but it's not really close to 0 either. So this would be known as a weak but positive correlation. We have to note the sign of the correlation too. We can either have a positive Pearson correlation, which indicates a positive relationship, or a negative sign, which would indicate an inverse or negative relationship. So the relationship between density of dentists and proportion of kids receiving preventive dental care is positive 0.319. That's the signal. But is the signal statistically significant? That's what the p-value answers for you. So in this sig row, the p-value here is 0.022. We're going to test the same thing, but we're going to use Jamovi, and because there's a different subroutine that they use for the computations, the p-value will be slightly different from 0.022, but it will be close. So it's a weak correlation, weak and positive correlation, that is statistically significant because the p-value is less than 0.05. Yes?
So on the 0.319, you said it's closer to 1 than it's...
The more, so these guys look like they're scattered, right? But it does kind of look like there's a positive increase, that as x increases, these dots tend to go up on the y-axis. But because they're not following very closely a straight line, that's why this number is not close to 1. If these dots were closer together following a straight line, this number would be closer to 1.0.
So it would make it more linear.
Yes. So it's still linear, but very loose. There's a lot of, so every single dot here is an observed value. But once we draw a line on here, that's the ideal line. And we want all of these guys to be on that line. These are observed, but there was supposed to be an expected. The expected observation would be, where would you be on that straight line? This is where you are right now, but the straight line says you should have been down here. So all of these guys, again, are observed values that we compare to their expected values. And that delta, that difference between what's observed and what's expected, is what tells us how close or far away from this 1.0 we are.
So we want it to be closer to 1. Close to 1.
We
As
want,
much as we can.
well, ideally, theoretically, if we're looking for, I only want one variable to account for the variance in another variable, yes, we want this to be close to 1. But our goal is if we had a pizza pie, and that pizza pie was a proportion of kids receiving preventive dental care, we know that individual factors are responsible for the proportion of kids receiving preventive dental care. One of those factors we think is the density of dentists or availability of dentists in that area, right? So that would be one slice of the pizza pie. And it's our goal to find out what are the other slices of that pizza pie so we have a whole pie. That's the regression model we want. So we don't really want this, ideally, to be 1.0 unless there's only one variable that accounts for all the variance here. We know that that's not true. So our real goal is to find out where are all the other pieces of pie. Here's one. Now where are the others? So this might be good enough. We'll put this in the model and see how well it does. That's next week though. Right now we're just doing correlations, kind of find out if you're significant here, that means you're going to be a candidate for a piece of pie slice. Maybe you'll fit, maybe you won't fit, but we'll find out later. So that 0.3 that we have, we're going to call that a weak association. And so anything that's less than 0.3 or 0.3 and lower, let's call that strength of association small or weak. Okay. If it's between 0.3 and 0.5, we'll call that medium. The strength of the association is medium or moderate. So we go from weak to moderate. And anything above 0.5, we'll call that large or strong. Large or strong. And again, the closer those dots, those observed values are to looking like a straight line, the stronger the linear relationship is between those two variables. So in the top left of this quadrant here, we have an R value. So we learned about Z, T, F. Now we're learning about R. These are all statistics. So the correlation is R. When the R value is 0.7, our scatter should kind of look like this. There's our best fit line. We see some of the observed values are close to this best fit line, some are a bit further away. But in general, if you look at the scatter, they kind of really fit a line. All of the observations are not on the line. Again, some are close, some are further away, but they're fairly close to this best fit line. That's why our R value is 0.7. Is that weak, moderate, or strong? That's strong. 0.3, you can see that the observations are a lot further away from the best fit line than they were for 0.7. That's why this 0.3 is considered to be weak. It indicates a weak relationship. It's still linear. See, they go up, but it's weak. They're not very close to this best fit line. Now this is the best fit line because if we were to tilt it up or down, if we tilt this up, then that means these guys are a lot further away from that best fit line, and that makes our deltas look even bigger. If we tilt or make the slope for this line down here, then that means these guys are a lot further away, and then again, that delta becomes a lot bigger. So this is the best fit line because it minimizes how far away all these dots are from that line. That's why we call it the best fit line. It's the best fit because it minimizes all the deltas. Yes?
So, so if the R value is closer to 1,
Closer to 1, okay?
does that mean there's more of a relationship between the x and y axis?
That means there's still a relationship. It's just it's a stronger relationship, and it's a stronger relationship. Now it's indirect how we're going to answer that. It's a stronger relationship because now we see that this line minimizes all of those the deltas. Look how close that dot is to that line. So that delta is going to be really tiny. So we know that this variable accounts for a lot of the variance in this variable, such that what's left is only a little bit that's unaccounted for. So our question is, what other slices of the pizza pie do we need to get to remove all these other deltas? That's what the regression tries to do. It says with one variable, now you have this fit, but you have all this that's left over. So now we have to think about what else could we get that would account for what's left over. Then we get another variable. And after we do that, then we might get something even stronger, and then we say, okay, is there anything left? Anything left, we try and find another variable, to the point where we say there aren't any more variables that account for any more of the what's left over. So what's left over goes in a bin called error. That's just what we can account for. Everything else can be accounted for by these 3 pieces of pie. Maybe it's a really large pie with only 3 slices. What's left, we don't know where it is. We can't find it. So one of our variables in there might be really strongly correlated. Another of our variables might be correlated but not be as strong. But once we put it all together, we'll get what's called, we'll take this value and then we'll square it. When we square this r value, we get what's called an r squared value. That's a coefficient of determination. And it's the actual amount of variation in our dependent variable that our model can account for. It's really exciting. So we do that next week. This is just the building blocks. Just the building blocks. Now for the correlation coefficient, we've been talking about dependent variable and independent variable in our x and y. But for correlation, it actually doesn't really matter what your x and y are. So we can take x and flip it and make it our y. We will still get the same correlation value. So with correlation, doesn't matter. But with regression, it does. With regression, we have to say what our dependent variable is and what our independent is. But for correlation, it does not matter what your x and y are. If you flip them, you'll still get the same r value.
Where does it matter?
Regression, that's what we do next week. So in regression, we're saying I'm trying to predict something. With correlation, I say I'm only trying to correlate 2 variables. So when I say I'm trying to predict something, we really need to know, well, what variable you're trying to predict. With correlation, it doesn't really matter. Like dancing, doesn't matter. Well, maybe it does. Who takes the lead and who doesn't take the lead. But that's old-fashioned dancing. You guys don't do that anymore. Everyone takes the lead in millennial dancing. All right, so what are our assumptions? So to make this work, our first assumption is that the variables have got to be ratio level. That is, it's got to be the kind of variable I can do addition, subtraction, multiplication, division. So if both of your variables can do that, it's a good candidate for correlation if you're interested in correlation. Next, the data's got to be normally distributed. If they're not normally distributed, then we won't be able to get a map that allows us to fit a linear model. So our x and our y, both of them have to be normally distributed. Third, there's got to be a linear relationship between the two. Otherwise, if we try to fit a best fit line on here, our understanding of what the real relationship is isn't accurate. Okay, so if it's a non-linear relationship, yeah, we might be able to get a line to fit it, but it's not going to be the best approximation of what the real relationship is. So if we're going to try and fit a line, the scatter's got to look like a linear relationship. Okay. Then finally, there's got to be homoscedasticity of the data. What do you think homoscedasticity means? Same something, right? Same statistic. Which specific statistic? Yes. Oh, I saw a hand. No, go share it. There are no crazy answers. All answers. We'll take them all.
I think it has to go with like the pattern.
Ooh. Yes. But the pattern of what now? Because you're both right. What pattern has to stay the same when we look at these guys? Ooh, I heard it.
Scatter.
Yes, the scatter, the variance. So if we see that there's a wide amount of variance down here, we need to see that there's a wide amount of variance the whole way across. It can't be wide down here like bell bottoms and then really nice and tight up here. Doesn't look great, unless it's the 70s. But today does not look great. So it's got to be uniform. That's homoscedasticity. The variance has to stay the same the whole way across this structure or this sequence. That's homoscedasticity. That'd be like the same sequence, same variability, same structure across this whole sequence. Heteroscedasticity is when it's not the same. So as you look at your scatter, and you say, yeah, it looks like it's about the same the whole way across, then you have homoscedasticity. If it looks like it's wide down here and skinny up here, or skinny down here, and then wide up here, or wide in the middle and skinny down here and skinny up there, those would be examples of heteroscedasticity. Okay? So we've got to have these 4 assumptions in order for our correlation, our correlation value to be a good fit for what we're looking at or what we're trying to test for. So if we try to do that with this data here, density of dentists with proportion of kids receiving preventive dental care, let's see if our assumptions fit. First, are both of the variables ratio level? That is, they're measurements in which we can do addition, subtraction, multiplication, division. I'm seeing head nods, yes. Second, are the data normally distributed? We've looked at them before. One of them is, one of them was not. Kind of looked like it was bimodal. Slightly skewed, but maybe bimodal. And what we're going to need to do is make an assumption that, well, yes, it's maybe not normally distributed, one of the variables, but our data is going to be robust enough to kind of overcome that. We still think our conclusion is going to be adequate or accurate. And I'm going to show you how we can hedge against that. Third, is there a linear relationship between the 2 variables? Yes, we can. But some of you are a bit more eagle-eyed and you're saying linear here for sure, but then it seems to round off. But for the sake of our purposes, we're just going to assume, we can fit a linear relationship. But it looks like it increases. As x increases, y increases in a linear fashion. Okay. And then finally, is there homoscedasticity? It doesn't look like there's homoscedasticity. It looks like this variance widens as it increases, as x increases. But we're going to have to go with the data that we've got. So what's most important is that you share what you found. Data's ratio, one of them is normally distributed, the other is not, but is probably robust enough to continue. There appears to be a linear relationship, but that linear relationship appears to be concentrated for the lower density of dentists than for the higher density of dentists. And there appears to be heteroscedasticity of the data, but maybe not so bad that I would not trust my findings. As long as you're honest and transparent about what you see, I know what the assumptions are, I'm just letting you know when they fit and when they don't fit, then others are free to make a decision as to whether they agree with your conclusion or not.
So whenever we turn this assignment in,
Yes.
this is the format that you want to.
Exactly. Just state what you see. It's okay if you say, no, it does not look like there's homoscedasticity. It looks like there's heteroscedasticity. That's fine. Just go ahead and complete the assignment. As long as you say what you see and it's accurate. Yes?
Can we go through those one more time?
Absolutely. So x and y, are they ratio level? They are. So this is the density of dentists. We can add and subtract, multiply and divide. Proportion of kids receiving preventive dental care, same thing. All of our mathematical operations are available to us with this kind of data. So they're both ratio. Are they normally distributed? Now we can test for that. What test can we use for normal distribution? That's right, Shapiro-Wilk. And one of these we've looked at, and that was the proportion of kids receiving preventive dental care in 2015-16, and it was not normally distributed. It looked like it was bimodal, actually. But we're going to proceed as if it is normally distributed, but we know it's not. We've tested. Shapiro-Wilk said, no, it's not. Density of dentists, I don't believe this is normally distributed either. Okay. Now what we can do is, those earlier slides, we can apply a mathematical transformation. So for example, if I took the natural log of density of dentists, I can get it to actually look like it's normally distributed. All I did was take the natural log. Every single value that I have for every state, take the natural log of it. Now I have this new variable, natural log of density of dentists. Now when I run it through Shapiro-Wilk, Natural log of density of dentists looks like it's normally distributed, and the p-value would be greater than 0.05. I don't expect you guys to do that, okay?
Yeah.
No.
You left.
But I do expect you to say, I've ran this variable untransformed through Shapiro-Wilk, and it's not normally distributed. Simply state that. Same for this guy too. Then finally, homoscedasticity. The variance appears to widen at this point and narrow and then widen again, and that would be an example of heteroscedasticity. We do not have the same variance over this entire sequence. Yes?
Is there a value or test we can use to test the homoscedasticity?
Homoscedasticity? Yes, there are a few, but I wouldn't want to introduce them in this course. They're hairy.
So we just do it by what we see?
Just visually, yeah, just visually. Right. We could actually apply some code to Jamovi to run it, but again, it's not a standard function in Jamovi. But in R, we can definitely call functions in and run that. But I don't want to introduce any programming into the class. What's that?
So let's not do that.
Let's not do that. All right. Doing good so far. Or doing well so far, I should say. So how do we report our Pearson correlations? This is the text that you would use. Pearson correlation was performed to determine the relationship between density of dentists and the proportion of kids receiving preventive dental care. There was a weak positive correlation between density of dentists and preventive dental care among kids, which was statistically significant. So we're going to say I use an R, because it's the Pearson correlation, R, and in parentheses you can either put the actual sample size, n equals 51 or 50, whatever your sample size is, or you can put the degrees of freedom. So the degrees of freedom I have here is 49. And then you put what your R value was, which was 0.312. And finally, after a comma, what was the p-value? Here it's 0.026. Using another program, it was 0.022. Using Jamovi, it's 0.026. Conclusion is the same. We reject the null hypothesis, which is that there's no correlation between these two variables. The alternative hypothesis is that there is a correlation. Okay, so null hypothesis, no correlation. R equals, what value do we have for no correlation? 0. R equals 0. The alternative hypothesis is R does not equal 0. It's some non-zero correlation. Might be positive, might be negative. Here, in this case, it's positive. Okay, so this is what you want to be able to write at the end of your correlation. So our goal, again, if we put this in the larger context of what we're trying to do, is to try to find out what's happening in the U.S. before and after ACA, specifically with oral health. So we have some data in which we can take a look at that. And your goal will be to characterize the correlations between preventive dental care, and that's for the kids receiving preventive dental care in the past year, with WHI. Now, WHI is those without health insurance. What do you think? Let me back up. Tell me what you think the relationship between density of dentists should be with proportion of kids receiving preventive dental care. What should this relationship look like to you? Positive relationship. So as the density increases, the proportion of kids receiving preventive dental care should increase. That's what you'd like to see. Anyone else? What would you like to see?
I would like to see
Sorry?
the scatter and even across the cluster. So almost, man, that word almost said that.
Oh, you want to see homoscedasticity?
Yeah.
Yeah, okay.
Something
Okay.
else that I would like to see, like
Okay.
the
Okay, so let's swap out the y-axis here and let's put those without health insurance. This is the proportion of people without health insurance. What relationship do you want to see between that variable and the density of dentists in that area? What would you like to see? 0, okay. Describe that. What does that mean?
That means that it doesn't matter whether or not they have health insurance.
Whether you have health insurance or not,
The
density of dentists won't change. What do we think is actually happening? Let's think about from the business standpoint.
Yeah, insurance.
If you can't pay for my services, am I likely to want to practice in that area? No. So the density of dentists might be related to whether you have health insurance or not. So we'll run it and kind of see what we have, what we hopefully would like to see versus what actually is. What about the second? Density of dentists with preventive dental care. We've got that one. And then what about without health insurance and the density of dentists? What relationship do you expect to see? Is that the one we just did?
Yeah.
That's the one we just did.
So negative?
What about the first one? Without health insurance and preventive dental care. So the proportion of kids receiving preventive dental care and health insurance, or those without health insurance, what relationship do you expect to see? An inverse relationship? Okay, describe that. As the proportion of kids receive preventive dental care increases, or actually we start with the other one. As the proportion without health insurance increases, what do you expect to see with the proportion receiving preventive dental care?
Other
Okay,
way.
but what do you want to see?
Does it stay the same?
Maybe the same thing. That as the proportion without health insurance increases, we hope that it has no effect on the relationship or the proportion of kids receiving preventive dental care. We hope that that stays high, regardless of whether you have health insurance or not. So we hope that density of dentists would stay high in an area without any relationship to health insurance, but that's probably not the case. We also hope that the likelihood of you going to see a dentist for preventive dental care is not related to whether you have health insurance or not. Well, we'll see if that's the case with the data we've got. All right. So in order to do this, let's take a look at Jamovi. Are you able to open the file that was sent to you?
I don't have a computer.
This last slide, do we need to keep this because we don't have
No.
this?
You can take notes on it, or I can send it to you. But again, this is just, we'll have this for next week when we do the regression. But right now, I just want you to take what we do today and put it in the larger context. We're still trying to figure out what's happening based on ACA. Because we're going to be able to do these correlations after 2010. We can also do these correlations before 2010. We want to see if they stay the same. That's not it.
Daniel, how did we do this last time?
Sorry?
I'm talking.
And yeah, I've got it. So we want to run correlations between the most recent data for those receiving preventive dental care and the most recent data for density of dentists. So what we want to run is up here in this regression tab, and the first option I'll get is for a correlation matrix. Okay, so I'm going to go up to regression, and I'm going to select correlation matrix. Again, regression and correlation matrix. All right? When I select correlation matrix, I'm being given an option to put in as many variables as I need in this window. Okay, we're only going to put two in though, and that's the density of dentists and the proportion of kids receiving preventive dental care in 2016. Just those two. So density and kids prev 2016. Oh, yes, so 1 was west, 2 was midwest, 3 was south, and then 4 was northeast. Okay, so ignore what I've got up here, and we'll focus our attention down here. We'll see a very simple correlation matrix, but we need to add some information to that. So over here in the top left, underneath our variables window, we'll see what's called correlation coefficients. And Jamovi is asking us, what kind of statistic do you need? Well, we need a Pearson correlation coefficient, so we select that. But underneath that, you see two others. And they're called Spearman and Kendall's tau. These two are correlation coefficients. However, these are called non-parametric correlation coefficients. In other words, they don't ask us to make the same assumptions about normality and homoscedasticity that Pearson does. So if we want to see how robust our conclusions are, when I don't make those assumptions, we ask for Spearman and or Kendall's tau. What I want you to do is select Spearman. And what we do is we compare the results between Pearson and Spearman to see how robust our results are. Does that kind of make sense? Because we're concerned about our assumption. Oh, I know my data is not normally distributed. Or it looks like I've got heteroscedasticity instead of homoscedasticity. Can I still run the correlation? Yes, you can. Just let's compare though to Spearman, which Spearman says you don't need those assumptions, but it's going to cost you. It'll cost us some power. You want to see if, despite that it costs me some power, can I still get meaningful results? That's what Spearman will do for us. Pearson is stronger because Pearson says if you can meet these assumptions, I can really find that signal. Spearman says you don't have to make those assumptions, and I'll try, but there's a limit to what I can do. But if I see it, I'll let you know. So let's ask for Spearman. To the right of correlation coefficients, under additional options, we definitely want to report significance. Those are the p-values. We want to flag significant correlations, which will mean more to us when you've got, let's say, a dozen or more variables that are trying to correlate to each other, and you're just looking for where are the significances. And then finally, confidence intervals. We always want to build a 95% confidence interval around the estimates that we're building. Bottom row of our options for the hypothesis that we're going to test is the two-sided test. Are they correlated? We're not going to look for only a positive correlation or only a negative correlation. We want both. So we'll pick the top radial button. Then over for plots, ask for a correlation matrix and the additional statistics. Mine is still running. You should get. Why is mine not showing it? You should get a scatter plot here, but
I did.
you did?
We have.
Okay. There we go. All right. So let's look at our top correlation matrix. Again, it's an identity matrix, so there's half of it, we don't expect to see anything. Density with density, there's no correlation to run there. Kids Prep 2016 with Kids Prep 2016, we don't expect to see anything there. All right, and density with Kids Prep 2016, we don't expect to see anything up here because we already have it down here. So if there are any redundancies, it won't be reported in the matrix. Okay, so don't be concerned if we see a lot of blank spots in our matrix. So let's focus on the data that we've got. Our Pearson's R, which is the correlation between the proportion of kids receiving preventive dental care in 2016 and the density of dentists in that same year, is 0.312. That's what you already reported in that last slide. The p-value for that was 0.026. Again, you've reported that. So this is how you get the data that you need to report. This is a positive and weak correlation, and it's statistically significant. Now, are we sure that 0.3 is the correlation between the density of dentists and the proportion of kids receiving preventive dental care? Are we 100% sure? No, we're not 100% sure. So if I'm not 100% sure, how would I tell you the degree to which I am sure? Confidence interval, that's right. The confidence interval, the 95% confidence interval says, I'm reporting the correlation as 0.312, but honestly, the true value is probably somewhere between 0.04 and 0.541, and that's a really wide range. We're saying essentially that the true value, the true correlation between these two, is somewhere close to non-existent to moderate. It's a big range. I'm reporting it as weak, but it's probably somewhere between it's not there to moderate. Am I 100% sure? No. And that's why we report a 95% confidence interval, because this is all sample data. Now the 0.312, we already know there are a couple assumptions I was a little sketchy on. Can I run an alternative statistic that does not require me to make so many assumptions about, let's say, the normality of my data or the homoscedasticity? If I use Spearman's rho says, okay, maybe you're not as strong as 0.312, but what we measure is 0.288. That's in the ballpark. It's still a weak correlation, not as strongly weak, but it's still weak. And it's still significant. What's the p-value? 0.041. It's still less than 0.05. Okay, so even though I could sacrifice, or I had to sacrifice certain assumptions, and I lose power, Spearman still says that, hey, the signal's strong enough that it's there. It's weak, but it's there, and it's significant. So I feel confident that if I report a Pearson's R, and I know that my assumptions are a little sketchy, I know that I'm reporting a weak but statistically significant correlation, and I feel confident about that. Because with Spearman says weak but statistically significant correlation. Same conclusion. And you can use this figure down here, ignore the density, so you can actually take the density off. You can use this figure down here to demonstrate the scatter and the best fit line. And in this gray, we have the 95% confidence interval around that best fit line. Okay. In your write-up. Okay. Yes.
What does the rho value have to be for it to be significant? And
You can have a very significant rho value and the p-value not be statistically significant. You can also have a very weak rho value and it still not be statistically significant. So the rho value cutoffs will be just like the Pearson R cutoffs. In terms of 0.3 and 0.5 is the thresholds for weak or strong, and middle is moderate, and below the 0.3 being weak. So both of these are fairly weak. The 0.312 and 288, they're weak correlations. You can interpret Spearman's rho as you would Pearson's R. They both go from 0 to 1, absolute values. If it's negative, it's an inverse relationship. If it's positive, it's a positive relationship.
So what if the Spearman's is way off from the Pearson's? What does that mean?
They're not typically usually way off, but there are times when there'll be a considerable distance between them. There are times. In that case, I'd say you probably don't have a linear relationship. What Spearman's does is it takes your data and it ranks it. So it could care less what the actual values are, it simply puts them in position and order. It says, do I get the same rank on one variable as I do with the other? And with the comparison of those ranks, then it gives you a Spearman's rho value. If your data is not normally distributed, right, then you might get this really weird, perhaps a really strong Pearson's R, and then a really weak Spearman's rho, because Spearman's rho says, I don't find a linear relationship between the ranks at all. But because of this funky parabolic relationship, you might get a strong Pearson's R. That could happen. But typically they're not too far off from each other. Typically. Yes?
You said if something's negative, then it's negative correlation. Which number were you pointing at?
Oh, these are the correlation values. So Pearson's R. P-value is never negative. Confidence intervals can be negative based on what we're measuring, but the R values, yes, they can be positive or negative.
So if R is negative, then it's a negative correlation.
You got it. Negative or inverse. Yeah. We're going to see some examples of those if we start to put in additional years. So why don't we do that? The first one is we wanted to look at WHI with preventive dental care. So let's go back to our matrix. The first thing we should do actually is take a look at our WHI variables and start to understand them a little bit better. So let's go to exploration, descriptives. And go all the way to the back of your variable list. And let's take 2008, 2011, and 2013. And for our stats, we'll ask for standard deviation and variance in addition to what's already selected, Shapiro-Wilk, which will tell us if the data is normally distributed. And for our plots, we'll ask for a histogram with the density and maybe box plot as well. Let's see what we see. 2008. Those without health insurance. What was the value? What was the mean value there? These are proportions, so if you multiply by 100,
9%.
yeah, it's about 9%. The proportion without health insurance in 2008. What about in 2011? What happened to the value? Did it increase, about stay the same, or decrease? Went down from 9% down to about 6.8%. And then by 2013, any additional change or movement? Down a little bit, 6.5%. So what happened after our ACA time point of 2010, or before and after 2010? Yeah, the program was expanded, so we see what we think might be a related decrease in the proportion of people saying, I don't have access to health insurance. So if you're a policy analyst, you might say, okay, we've done our job. We have decreased the proportion of people who say they don't have access to health insurance. What else? What other statistic would you want to look at to see if you made an improvement as a policy analyst, if you're responsible for helping bring ACA to the country? Standard deviation. What do you want to see with the standard deviation?
You want to see it get tighter.
You want to see it get tighter. Do we see that? Standard deviation in 2008 is about what? 0.04. Then what happens after ACA?
Decreases.
Drops to about 0.03, but then go up further. What happens? Down to about 0.028. So standard deviation got tighter over time. So not only did it decrease the proportion, we also see that it's tighter, meaning maybe in 2008, this is far too heterogeneous of a population, right? We have a subgroup up here. It's a lot of them saying, well, there's not a lot of them, but this is pretty wild. Between 15 to 20% saying, I don't have access to health insurance, but it's a subgroup. Then we have this other subgroup that's somewhere between 10 and 15%. Then we have another group that's lower than 7 or 8%. It looks like there are 3 subgroups here when it comes to those without health insurance. So instead of it being one country, one nation, it looks like there are 3 populations actually. When we go to 2011, just after ACA, describe what you see in terms of characterizing that distribution. Does it look, which is more heterogeneous, 2008 or 2011? 2008. So by 2011, the distribution does not look like it's so heterogeneous. It doesn't look like I have 3 distinct subgroups, maybe 2 subgroups now. What about by 2013? What do we see? Even less heterogeneous. Now, slightly skewed, but far less heterogeneous than what we saw in 2008. So as a policy analyst, as you're looking at the data as it comes back to you, you might be saying, looks like we're making progress here. We've decreased the proportion of people saying they're without health insurance, and it looks like it's a much tighter, more uniform distribution now than it was previously. So now if we intervene, maybe those interventions might work throughout the country instead of causing more subgroups. Okay, cool. So now let's take WHI, that is those without health insurance, and correlate that with the proportion of kids receiving preventive dental care. What we'll do is we'll keep 2008, 11, 13 here. Oh, sorry, let's go back to regression, correlation matrix. Let's put those guys back in. 2008, 2011, 2013, and let's take Kids Prev for 2007, 2011, and 2016. Okay, so those without health insurance, 2008, 11, and 13, and the proportion of kids receiving preventive dental care, 2007, 11, and 16. Do we have everything we need? Do we have everything we need over here? Let's get Spearman. What else?
Flag.
Well, the confidence interval.
Thank you. And the confidence intervals, correlation matrix, and stats. We don't need the density. Good? Oh, hold on. Not going anywhere. Here we are. Okay. All right. So if we go to this first column of data, that's the without health insurance in 2008, we want to drop down to the first row that will be meaningful to us. So we're not interested in correlating it with itself or correlating it, WHI with any other year. We want to start here with Kids Prev in 2007. Wow, what do we see there? What do you guys see? What's the correlation between the proportion without health insurance in 2008 with the proportion of kids receiving preventive dental care around that time point?
Negative.
There's an inverse relationship. How strong or weak is that relationship? It's strong. And you're measuring it as 0.7, 0.715. If we're not sure about any assumptions we had to make about normality or homoscedasticity, and we use Spearman, what's Spearman telling us? Ooh, maybe slightly stronger at 0.73. Are they significant correlations? Yeah, they are. Here the p-value is less than 0.001, and here the p-value is less than 0.001. So what kind of strength of significance is that? What kind of evidence?
Significant.
Overwhelming evidence, I think I heard it. Yes, overwhelming evidence against the null hypothesis that this rho, or Pearson's R, is 0. So the null hypothesis is the correlation 0. We measure it as 0.715, and the p-value, it's so small because it's saying the likelihood that chance is responsible for what you're observing is really low. It's a very low probability. Does this fit what you expected to see? Explain what an inverse relationship between these two variables actually means. So what are you going to put on your x? What will you put on your x? Kids Prev. So as the prevalence or the proportion of kids receiving preventive dental care increases, how is it related to those without health insurance? So as proportion increases, what's happening to proportion without health insurance? It's decreasing, which intuitively makes sense. Does that hold true after ACA? What happens after ACA? So this is 2007, 2008. That's before ACA. After ACA, let's go to 2011, and we're going to drop down to Kids Prep 2011. What do we see? It's about the same. It's still fairly high. The correlation is pretty strong, 0.7, meaning that there is a fairly tight relationship between having health insurance and your kids receiving preventive dental care. Maybe because those who have health insurance probably also have dental insurance or are willing to pay out of pocket. Maybe they have the funds to do so since other healthcare needs are being taken care of or being subsidized. So we see that it's 0.7, and if we adjust because of our assumptions maybe not fitting so well, if we look at Spearman's, what's our correlation value? 0.668, and they're both highly significant. Right? Okay, so it still holds right after ACA. What about as we let ACA kind of mature and develop? So now we move out to 2013, and we're going to take the latest time point we have for Kids Prep. What's the relationship there? We drop down, and what do we see? It's finally dropping. That is, the proportion of kids receiving preventive dental care is not so dependent upon whether you have health insurance or not. Right? So now it's 0.428 instead of being 0.7 or 0.715. Is that what you want to see? That the proportion of kids receiving preventive dental care, which you know has increased. From all these 3 time points, we know the proportion of kids receiving preventive dental care has increased, and now we see that it's not as dependent on whether you have health insurance or not. Sorry? Well, that's the question. All we have is data. But as analysts, your first job is take the data, build a narrative with the data, and then where you have gaps, like the why gaps, what studies could I conduct, or what information do I need to collect to address those gaps? To build a more tightly defined narrative. But right now, what we know is proportion of kids who receive preventive dental care has increased, or was kind of low before ACA, but then kind of increased after ACA. And then when we correlate proportion of kids receiving preventive dental care with those without health insurance, we find that in the beginning it was kind of a tight relationship, but then as ACA matures, it's not so tight, that dependency anymore. So if we build our model next week, the variables we might want to have in our model for those receiving preventive dental care would be first, whether they have health insurance or not, and density of dentists. So let's build density of dentists into here as well too. Let's evaluate that. So density of dentists, let's take the kids prep out first. And let's build our density of dentists in. So we'll take 2007, 2011, and 2015. Sorry, I got region in there. Take that out. Okay? And what do you expect to see in terms of the relationship between density of dentists and those without health insurance? We hoped that there would be negative or independent. Like zero, no relationship. Yeah, maybe no relationship. That's what we want to see. I make money whether they have health insurance or not. But what we think is probably there is, if you can't pay for my services, I'm probably not going to be there. So we expect a lower density of dentists in that area. 2008, we're going to compare it with 2007. And what do we find? What's the correlation? It's negative, but it's weak too. 0.341. And then if we use Spearman's Rose says it's probably weak to moderate, but they're both saying that it's statistically significant. Question is, after ACA, what happens to that relationship? So that's 2008, 2007. When we go over to 2011, what happens to the relationship? So it goes from 0.341 negative to 0.321. Didn't change much, right? Still a weak correlation. And as we allow ACA to mature, do we see any change in that relationship? So we go out to 2013, go to density of dentists. What happens to the relationship? Compared to where it was in 2008, what happens to the relationship? It gets a little stronger. What does that tell you in terms of the relationship between density of dentists and those without health insurance?
Inverse.
Sorry?
It's inverse.
Right, so it's an inverse relationship, but the size of that relationship is changing slightly. It's getting a little bit stronger. What does that tell you about that relationship between density of dentists and those without health insurance? What does that mean to you? This corner is kind of quiet.
Yeah, right.
Yeah. What do you guys think?
For which one?
The last one. So you see here, the correlation between being without health insurance and density of dentists goes from 341 to 321, right after ACA, to 448. What does that mean to you? What does that mean? The relationship is getting stronger, right? What does that mean to you?
So it's independent.
Is it more independent or more dependent? So it's more dependent, but what does that mean? I mean, if it's real, what does this mean to you?
Implies causality.
Maybe. Okay, so the comment was brought up of causality. Correlation
It's not proof
is
causation.
not causality, right? Umbrellas don't cause rain,
Oh, man.
but there's a strong correlation between the two. If you bring an umbrella out, it's probably because it is raining, not because bringing umbrellas out causes rain. So correlation, not causation. They're just related to each other. But what does this mean to you?
Dentists are offering free healthcare.
Dentists are offering free healthcare, and that's how they're staying in business. That's why the density is higher. There's a hand in the back.
Even that patients, dentists are having more affordable dental care, so more people are seeing the dentist.
Okay, possibly. So the proportion without health insurance, is it changing over time? Yes, the proportion without health insurance is decreasing over time. That means for those who are still saying that they are without health insurance, right, so what's happening in terms of that relationship with the density of dentists?
The density of dentists is becoming more dependent on whether or not
Yeah, the density of dentists is becoming more dependent on whether you have health insurance or not. Or at least for those who don't have health insurance, how are you going to receive care? So density of dentists, are they relying as much on those who have health insurance?
Yeah.
So here, this suggests that after ACA, that although there's a proportion of people who are saying, now I have the funds or resources to supplement and maybe receive preventive dental care, at least for my kids, it's saying that there's still a stronger group, though, we're saying we're still highly dependent on whether you have health insurance or not, at least those that remain in the market without health insurance. So it's becoming tighter. It's becoming tighter. Yeah, the correlation is becoming tighter. Maybe that's a good thing. Maybe one can spin that to trying to provide a certain kind of care, or maybe this can be spun as a reason why they need to bring dental care into these universal programs, if it has an effect on the outcomes that we all say is important. But as we saw before, there was a study that suggests it doesn't really matter if the kid gets their preventive dental care from the dental clinician or the medical clinician, as long as it happens. Maybe, maybe not. Like to see. Maybe it's cheaper through the dentist than through the medical route. Okay, so the final thing is we want to take a look at density of dentists with proportion of kids receiving preventive dental care. We take health insurance out and we put our kids' prep in. Are you guys pleased with yourself, with how well you understand the healthcare system now, at least from the effect of access and care on the outcomes for kids, or at least proportion of kids receiving preventive dental care? Had you considered the effect ACA might be having on that at all?
No.
Now you're considering it. Yeah. All right, so what is the effect that density of dentists has on the proportion of kids receiving preventive dental care? Is there a relationship, do you think? Okay, and what kind of relationship do you think it should have? What would you like for it to have? Inverse or positive relationship? Positive. And a strong one or a weak one?
Strong.
Strong. Okay, what do we have though? So if we look at 2007, we see that the correlation is 0.396 and it's statistically significant. Okay, so there's a weak to moderate relationship, positive, which means the more dentists there are, the more likely we are to find that kids are receiving preventive dental care. That's what we expect to see. Just after ACA, so 2011, we see that 0.396 turns into 0.328. It's still significant, but it's not as strong as it was before. And after ACA matures and makes its way throughout the rest of the country, by 2015-16, what do we find? Back up to 0.39. So the relationship hasn't really changed that much in terms of density of dentists and proportion of kids receiving preventive dental care. So the question you might have is, what does this relationship look like if I adjust for whether this area has health insurance or not? That's the regression model. So the regression model is, instead of having just a one-to-one look at the relationship, it's a many-to-one look at relationship. So now I get to adjust for the presence of other variables when I'm looking at one variable. So in other words, what you're asking is, if the relationship between density of dentists and proportion of kids receiving preventive dental care is 0.39, will it stay 0.39 if I adjust for health insurance and other variables? Or will it increase or decrease? And that's what we can do with regression. We can see, does this stay the same if I now account for the other pieces of pie? Yes?
So what does it mean again if we look at kids prevalence 07 to density 07 and look at those numbers and what is the what does it mean?
Right, so we're hypothesizing that the Affordable Care Act had an effect on these relationships. That was about 2010. So when we look at the relationship between these two variables, density of dentists and kids prep, or the proportion of kids receiving preventive dental care, before ACA and after ACA, We want to see if there's been a difference in that correlation. Has the correlation size increased or decreased? Well, what that means is that if ACA has changed that, then we might have an idea of how ACA or some other larger factor has affected these relationships that are important to clinicians. If there's been no change, that means ACA hasn't really affected that. So the question really is, how pervasive has ACA been in affecting the relationships between these variables? So we need to look before ACA and after ACA to see if there's been a change. And right now it's 396 before, and then just after it dips slightly to 326. I don't think that's really important. But then later it's at 390. So it appears like this relationship between whether kids or the density of dentists and the proportion of kids receiving preventive dental care is unaffected by ACA. So it looks like the proportion of kids receiving preventive dental care might be, one, partly due to density of dentists, but might have more to do with what's happening on the health insurance side. So even though there's ACA, there's still, remember we saw groups of people saying, I don't have access to health insurance. But how can that be? There's ACA, right? So for the heirs who are still saying, I don't have access to health insurance, there might be another barrier for why they're not seeing the dentist or their primary care physician. And oftentimes the two might be related, and not unlinked.
But isn't ACA, I mean, I'm not familiar exactly because I didn't get involved in it, but does that mean that they're still paying for insurance even though they have ACA? Or
Dental insurance probably, because it doesn't really cover dental.
Dental insurance.
Right, exactly.
That's what you're saying.
So, but if I'm saying, look, I have limited resources, but if now what I was putting into healthcare is now being covered by another program, I now have funds available for supporting dental care. Now, people making those decisions, maybe, maybe not. Maybe in certain regions they are, and others they're not. Exactly. But it's our job to try to understand that. So the purpose of this course is using data that's publicly available. Could we, one, learn statistics, and two, understand a little bit more about what's happening in terms of healthcare in our country and how oral health is related. Okay, so your homework assignment will be doing exactly what we've done, but not to this extent. So there are a couple years in which you're expected to do it, not all the years after ACA. And it's not with WHI in both of them, it's only with one of them. I will send the assignment out, and you'll have 1 week to complete that. Now next week, we're still going to meet on Tuesday. Monday's Labor Day though. So I won't be able to meet with the pre-docs. I got to figure out when to meet with those guys, have their last class, and then that's it. Once we have that last class, you have all the stats that you need to do your group project, and you also will. I need to meet with you and see your homework. The Cheryl Willard. I've got to see that before the class closes at some point. So whether you come by to my office or there's some other time to kind of see that, I'd like to see that. Yes.
So we have an assignment due on Friday,
This Friday.
and then we have this assignment due on Tuesday,
Correct.
and then we're not meeting during the finals week.
It's
'cause
going to be
just gonna
take-home.
take home. So then, okay, so then we're just gonna bring you our books some other time.
I need to see it. If you can't be bothered, okay, but then I can't give you credit for it. I want to give you credit for it.
I don't know if you noticed, but when you took the midterm, it
Yes.
says like pick 10 questions out of 12.
Yes.
It randomly picked for us 10 questions. It randomly
Oh, you didn't get to select?
No. we
Oh.
didn't get to select anything.
Okay.
Neither
You should
one.
be able to select.
Yeah.
I'll take a look at that. The assistant didn't tell me that. Okay. Yes. Yes, yeah, we do a project. So remember when you told me which variables? Yeah, exactly. But you couldn't complete that because you didn't learn all of the statistical procedures. Now that you will have all the statistical procedures, you did it. You just gave me the outline, but the actual data, now you're going to run it
When is that due?
at the end of the course. So with your final exam.
With the final exam?
Same date. Same date.
When are you grading the midterm?
You haven't received those grades back yet?
Not
On your Canvas?
Not the whole, there's some, but the
Right.
questions that we had to submit through Jamovi, those ones.
Okay, those
so
haven't
right
been
now I have
submitted.
like a 45 out of 100.
Ooh. No. No, don't
don't look at that grade because that can't be your grade. I will make sure that I'll make sure she gets on it this week. She's another student, but not in this program, somewhere else on campus. So, yeah, I'll make sure she gets it. She's a TA. Yes.
So the 10th of September is when the projects are due and the final.
Yes. Both will be due.
The 10th.
Any other questions? Yes.
I got confused. So we're not having my school.
We are meeting next week, but that'll be our last meeting.
And then you're checking our books next
If you bring it next week.
Oh, yeah.
If you don't bring it next week, then schedule some time to bring it by so I can see that. Other questions?
Can we put you in our pocket when we're doing our homework?
Unfortunately, this is a very big pocket. Unless there are goodies in that pocket, definitely not.
Goodies? What kind of goodies?
Oh, we'll tuck the chip.
Okay.
Other questions? No? Alrighty.
We need to arrange for us to work on that.
Yes.
We need to meet today
Yes, we do.
to make plans.
Yeah.
So,
We have to work on our dental health education.
yes, that one. We have like about 3 things to do this week.
Yes.
I wanna
Yeah,
do
we
it
have a lot.
by Thursday. So, we'll make plans. Tonight, we can go to Panera or your option, baby. So what I'm gonna need you to do is